record.
Yes.
Okay, here it is. Now I start. So it's a pleasure to present Jose Antonio Carrillo. First met him like when we were both PhD students in Spain. So he did his PhD in Granada, and then he was hired in Universidad Autónoma de Barcelona. But since he's very, very strong mathematician, he went to the Imperial College of London and then to Oxford. So now he's working in Oxford. He has several prizes and recognitions all around the world. And I will say that he's a very generous scientific. He always helps people, helps journals and that all. So you're welcome, Jose Antonio.
Thank you, Lucero, for the nice introduction. It's my pleasure. And yes, we know each other for a life, essentially. That's true. Today my talk is devoted to some research I have done in the last 4 or 5 years related to a particular aspect of aggregation-diffusion equations. And the particular aspect I want to focus my talk today is in explaining these two these two words, fast diffusion and partial concentration. So, but in order to get there, and since it's a very wide scope conference, I will make first an introduction of what this is all about. So let me see. Okay. Good. So now I can. Yes. First of all, I will make an introduction to the field and the problem that I'm interested in. Then I will put this a bit into context of the kind of problems that I will focus. And finally, I will really focus on the main aim of my talk today, which is in a particular regime of this family of equations called the fast diffusion Keller-Siegel model. And there I will show that, in fact, you can have a very interesting phenomena from my point of view, which is the concentration of the density in a point, but partially. So at the same time, you have some kind of absolutely continuous part of the density. And especially this will be a minimization problem. So mostly of what I'm going to talk today is in fact about especially the most specialized part about calculus of variations. Okay, let me see if I can manage to do this at the same time as I see you. For some reason, this doesn't work at the same time. Okay, good. Anyhow, so let me let me try. Okay, it's okay. So minimizing free energy. So that's the motivation about the origin of this kind of equations. So let's assume that we have an interaction potential. Like I hope that you see my mouse. So this that I'm denoting here by u. U is a function that is assumed to be regular, except maybe at the origin, where you can have some singularity. Even if I'm defining the value at 0 equals 0, and the only thing I'm assuming is that is symmetric. And then let's assume that we have an interaction between particles of this form. What does it mean exactly this? It means that I'm assuming that the particle xj is producing a force at the location xi just by its presence, like electrostatics of gravitational forces, but they can be model other things. So just the presence of the particle xj produces that force, and that force is given by gradient of the potential u, and that's why I call it the interaction potential. And then I'm adding all the forces acting on the particle xi by the presence of all the other particles xj with some weights that you can think about the masses of the particles, and this gives me the total force acting on the particle xi. And then I'm writing that xi dot is given by the minus the total sum of the forces. Why I'm doing that is because essentially what I'm writing here Our second-order dynamics could have introduced the second-time derivative of xi at assuming the inertia term is negligible, while keeping a friction, which is denoted by xi dot. So what you want is inertia-less particles with damping forces, okay? So that's why I have a first-order dynamics in principle for the evolution of these particles. But what I want to do is to analyze a model which is continuous for the density of particles. So I want to pass to the continuous model associated to these dynamics for particles. And that's the motivation of the kind of equations I want to understand. So if I now assume that rho Tx is really the density of particles at time t, could be the mass density or the probability density, as you prefer, then I am assuming that each infinitesimal part of the mass, rho at location y, produces a force at location x, which is given by minus gradient u of x minus y, and then I'm integrating. This gives me the velocity field at location x. So I'm mimicking somehow what I'm doing here at the level of particles. So what I'm expecting in the limit when the number of particles is large, you expect to have a dynamics for the density of particles, which is given by a continuity equation for the evolution of the density of particles, where the velocity field that drives the motion of the mass density is given by that formula, which in mathematical terms one can write as minus gradient of u convolved with the density rho. So it gives rise to this kind of non-local continuity equation. Okay, so this equation is usually referred as the aggregation equation. What is the aggregation-diffusion equation? Is written in this slide, in which I have now two terms. The blue term, the red term is what I had in the previous slide, which is the non-local term. And now I have a local term, which in the velocity field, I have a component, which is given by minus the gradient of certain nonlinear function of rho. Okay, why I do that is because I can also model, let me say in the previous slide, that typically the interaction potential is modeling any kind of force. It could be attractive or repulsive. From what it depends that is attractive or repulsive. For instance, if the u is a radial function, it's easy to understand that when the u is increasing as a function of the radius, this force, with the conventional sign that I have chosen here, this force means that at that distance where the velocity, the interaction potential is increasing, that force is attractive. While if the derivative of u in the radial direction is decreasing, at that, if these particles are at that distance, the force will be repulsive. So in some sense, this term encodes both attraction and repulsion. But we can decide that this only encodes attraction, and I can include the repulsion between the particles in a different way by a non-local term like this, which this is modeling the diffusion of particles that we can understand as a kind of a repulsive force between the particles. So then, what is the interesting question about this aggregation-diffusion equations, or one of them at least, is when does a balance between the attraction and repulsion happen, and what does it mean to have this balance? Okay, so let's focus first on what does it mean to have that balance. So now I'm coming back to some basic properties of this family of equations, which have this structure in the previous slide, a non-local term in the velocity field plus a local term that is modeling diffusion. I will make assumptions on P immediately that you understand that this term gives rise to a diffusion. So formally speaking, that model is in divergence form. So if we have good solutions for the PDE, we should have conservation of the mass. But not only that, because of the symmetry of U, you can prove that you will have conservation of the center of mass. And then this means essentially that the problem, in fact, we can see it also in terms of the free energy here in a second, is translational invariant. So we can fix the center of mass at some location. And in fact, there is this equation has a very interesting structure. It has a very importantly Lyapunov functional in the sense that, in fact, the equation itself can be considered as a gradient flow in infinite dimensions, a gradient flow in the set of probability measures, which today I'm not going to describe in detail, but there are plenty of papers and that people have looked at how to make sense of that equation as a gradient flow. But we can just realize that this is a free energy, this free energy that is usually called this function, the free energy of the system, is a Lyapunov functional for the PD, at least formally. We had to choose this phi in related to P in such a way that this is true. And in fact, we can see it formally in this way. The PD that I had in the previous slide can be written in this form. So it still is a continuity equation where the velocity field is given by minus the gradient of the variation of f with respect to rho. If we perform the variations of f with respect to rho that keep the mass of rho, that the integral of rho is conserved, it is not difficult to see that the variation gives rise to this formula. The variation will be u combined with rho, because this is a quadratic function in rho, while this one, it will give you just the derivative of rho. And if you choose the relation between P and phi in this way, that P is in fact the primitive of the phi second. So when phi second is non-negative, so phi convex, then you see that that term is going to give me a kind of nonlinear diffusion, and in fact it coincides precisely with the relation that that we need in order to write the equation in this form. So once we have written it in this form, it's easy to compute, at least formally, the time derivative of the functional along the solution, and just one iteration by parts using this formula gives you that it should be non-negative. Because what you get is minus the integral of rho, the modulus of the velocity field of the continuity equation, even non-linear, squared. So we expect this to decay along the solutions of this PDE. And now we can specify much better what we mean by a balance between attraction and repulsion here, between the non-local term and the local term in the PD, between the non-local term and the local term in the free energy functional. What we mean by a balance is that we can find non-trivial local minimizers of the total interaction energy. So when does a balance between attraction and repulsion happen? This is a very classical question that in some particular choices of this potential has been studied for many years. For instance, if the potential is the Newtonian potential, either attractive or repulsive, these, and particularly in the case of the function phi that leads to linear diffusion, which corresponds to the Boltzmann entropy, phi should be rho log rho in that case. In that particular case, it has been studied a lot, and it appears with different names in astrophysics or in chemotaxis, in math biology, as the Keller-Seeger model on semiconductors. So that's probably the most developed case. And there are other applications more modern of this kind of equations, of this kind of free energies that appear in economic applications, for mean field games, in fractional diffusion, for random matrices, and other questions. So for more general U and phi. Okay, so now that we know the kind of equations that we're interested in, let's focus more the discussion, and let's talk about a particular family of equations for choice of the potentials and the nonlinear diffusion. So let's take this kind of equation in which I'm assuming that both the potential, the interaction potential U, and the nonlinear diffusion P or phi are power laws. They are homogeneous. If I assume that both of them are homogeneous, so then I'm writing the first term as a kind of porous medium-like equation term, if you are aware about the porous medium equation. So then I take rho to the m as the power for the free energy function in the previous slide. And I'm assuming that U is also a power, is modulus of x to the k, at time divided by k, in such a way that this potential is always attractive, no matter what the sign of k is. K can be just larger than minus dimension, is enough. And I'm taking the convention that when k equals 0, I take x to the 0 divided by 0 by convention is equals to the log. Why this? To include the Newtonian potential in any dimension. As you know, in 2 dimensions, the Newtonian potential is the log. And also because it's the limit as k goes to 0 of this potential, if you just add the corresponding constant to which is minus 1 over k to this. By the way, and I'm putting also in front a constant chi in such a way that I can control the different strengths of attraction versus repulsion. So this just controls how large, say, is the second term with respect to the first term, in a sense. Okay, so because the two terms are homogeneous now, I mean, both the nonlinear diffusion and the interaction potential, it's not difficult to see that this equation has certain scalings. You can see it also in terms of the free energy in the previous slide. In fact, if I go to the free energy, this free energy, the two terms, the red and the blue, they have certain homogeneity. What do I mean that they have certain homogeneity? That I can take the profile rho in which I'm evaluating the free energy, I can scale it by some factor, call it lambda, and I scale it in a way that I dilate rho, but keeping the mass. So I define, say, lambda to the d rho of lambda x, which is just an scaling with the parameter lambda. Either if lambda is larger than 1 or less than 1, I will make it more dispersed or more concentrated. And by that, doing that scaling, I can see that this functional has certain homogeneity. And the same here. And in fact, you can check in this way that the only way in which both terms, they have the same homogeneity is when m is equal to this value. This is the case in which both terms scale in the same way. And then there are three different scalings in this equation. When m is larger than that, when m is less than that value, and the case in which both of them scale in the same way, being then the free energy homogeneous. And let me just explain, without reading all some of the references that I have here, let me just explain why I call these regimes in that way. When m is larger than that value, what happens in the free energy is that, if I go to the previous slide, what happens here is that this term dominates that term. The blue term dominates the red term. And what is, in which sense it dominates? It's in the sense that if I try to concentrate the profile by scaling it while keeping the mass, so by making it closer and closer to a Dirac delta at a point, then this free energy increases. So this means, in fact, that there is no any advantage of concentrating if you want to minimize the function or you want to decrease the energy around the solutions of the evolution PDE. So concentration will typically not happen in that case. While if you have the opposite effect, if the homogeneity of this guy wins the homogeneity against this one, then you have the opposite effect. When you concentrate the profile close to a Dirac, this energy decreases, so going to minus infinity. And in fact, then you may have concentrations. And that's just an intuition that you can make rigorous in each of these three different cases by looking at, I mean, in particular cases have been already established. So I will not go into that detail. So, but let me mention that essentially all of that is based on the existence of certain functional inequalities, which is very much related to my talk. So, and the functional inequalities that that appear are variations of what is called the Hardy-Liebel-Sobolev inequality that it will appear in a sec. So let me explain you what I said before again in words. In the case of the fair competition case that I call it in the previous slide, when you have this equality between K and M, in this case the free energy is homogeneous of a certain power. And this includes what is called the classical Keller-Segal model in 2 dimensions. When you consider the Newtonian potential, attractive Newtonian potential in 2 dimensions against linear diffusion. And in that case, it's known that there is a criticality There is a criticality in the sense that depending on the parameter chi in front of the non-local term, you can go from the non-existence of stationary states and the fact that solutions converge to a unique self-similar profile to finite time blow up, while the only parameter for which there are stationary states, non-trivial stationary states, is the critical one. Okay, so this happens. This exactly same behavior happens along the whole red line that I have here in this diagram. This diagram has M versus K on the x-axis, M on the y-axis. And then this line corresponds to what the red line corresponds to what we call the fair competition regime. Here is when K is negative, which is mainly what I was discussing till now. And then in the whole line here, the same behavior as I said in the previous slide holds. And then this division between diffusion dominated and attraction dominated is quite clear. But what we realized at that point, and that's where I will enter into the particular discussion today, is that the case in which K is positive, or when M is less than 1, so this quadrant over here where I have all these question marks, in principle, this red line over here may play the same role or not as before. Is the line of homogeneity. This is exactly true, but does it really play a role? What happens in this range here? So because the issue is that when M is larger than 1 and K negative, when you are in this area, then the two terms that are in the free energy, the non-local term is always negative, while the local term is always positive. And then if you want to prove that this free energy, the free energy associated to this model, is bounded below, what you need is a control of the non-local term by an LM norm of the density. And this is what the Hardy-Lidl-Sobolev inequality gives you. So the same kind of approach cannot work here, because you work out what are the sign of the two terms in the free energy. When you go below 1 for M and K is positive, they swap. The non-local term is positive, and the local term by the nonlinear diffusion becomes negative. So you want even to show that the free energy is bounded below, before even proving the system of minimizers, you need a completely different kind of inequality. And that's where we enter into the part in which I want to focus today. What happens in that range? Can we identify the different kind of regimes like in the previous case? And as I said, the inequality that you need is completely different, and that's the inequality, is what is called we call it reverse HLS inequality. We call it reverse HLS because, in fact, here, as you see, we are controlling the integral rho to the M by this kind of non-local term, which is a kind of non-local moment of the density rho, because K now is positive. And I'm not referring as this as any LM norm. This LM here is just a notation to say that the integral rho M is finite, because I'm not claiming that this has any Banach structure. It's not a Banach space, just that the integral rho M is finite. So I'm estimating the integral rho to the M by this non-local term modulo the L1 norm, and this alpha can be obtained just by homogeneity of this inequality. So is this inequality true? What we realized when we started to work on this problem is that there was already somebody that looked at these reverse HLS inequalities, and they were able to prove that inequality in a very particular case. By the way, here there are some typos. Instead of this capital N, it should be a D, this dimension. All the capital N's in this line should be this. Okay, so, and what we were able to do is to generalize much more the range in which this inequality holds true. We prove that this inequality is true for functions that are integrable, non-negative, such that the integral rho to the M is finite, if and only if M is larger than this value. d over d plus k, which has nothing to do in principle with the homogeneity regime that we had before. What's the reason of that? Let me show it to you in the parameter space, and then I will concentrate in a very particular question that I want to explain you which solution we found in a very particular range. But let me explain you the different behaviors here. So I will concentrate just below m less than 1. For m larger or equal than 1, things are easy, in fact, and they come back to things that are well known in previous cases. So the most interesting things here happen for m less than 1, as I said, which I'm marking two regions. First, the region 1 is the region below the curve m equals d over d plus k. First of all, let's place the line of homogeneity. The line of homogeneity that we had before, that was important when k is negative, is m equals 1 minus k over d, and is exactly tangent to this curve at k equals 0, m equals to 1. So it always lies below that curve. And why it's not playing any role in our case is because one thing that we proved, too, is the if and only if in the inequality, in fact, implies that this energy is, in fact, not bounded below for m less or equal than d over d plus k. So this is what we were able to prove, not only for equality, but also for less or equal than d over d plus k. The free energy is not bounded below. So that's why the homogeneity doesn't play a role. It's really true it's homogeneous, but it's already, the infimum is already minus infinity, so it doesn't give you any information. So that was the first surprise that we got. The second surprise that we got, it was the following. If I look now at the range between the two curves, m equals 1 and m equals d over d plus k, well, first of all, this 2d over 2d plus k is this red line is the only one in which people had obtained the reverse HLS inequality before. So that's our improvement is to have it for the whole range there. And the thing that we improve over that is this dark gray region that you have above this curve and above m equals d minus 2 over d. In this dark gray region, we can say more about the optimizer of the inequality. And the inequality optimizers are important because we proved that the inequality is equivalent to have that the free energy is bounded below. And the optimizers of the inequality will be the minimizers of the free energy. So saying things about the optimizers of the inequality was equivalent to identify properties of the minimizers of the free energy. So what you expect to be a stable point on the dynamics. And what we prove in the dark gray region is that the minimizer or the optimizer, the minimizer of the free energy, or the optimizer of the inequality before, is an L1 function, such that the integral rho to the m is finite. So it's an interval function. There is no any concentration anywhere. While in the white region, the interesting thing is that may have some Dirac concentration at the origin. And this I will try to explain in this theorem that we proved some years ago. I will explain the references at the end. So what we prove really, in order to minimize the free energy, is that when m is larger, still larger than d over d plus k, we can show that there exists a minimizer, a global minimizer, modulo the translations, but it has a very particular form. It's a gradually decreasing function interval, and possibly it has a Dirac at 0 with certain mass, which is between 0 and 1. Here I'm assuming that I'm minimizing over probability measures, and I'm assuming that the interval rho is 1. So the question is that in that dark gray region that we had in the previous slide, we proved that this possible Dirac at 0 doesn't show up, that m star in that dark gray region is just simply 0. But then the question is, do we have a concentration in the white region? Can this really happen here? Can we have a minimizer that partially has a mass, a Dirac mass at 0 with partially the total mass of the density? And the answer to that is that yes, this can happen, okay? And let me explain that to you in the last minutes of my talk. So I give you some ideas why this is true. So so for concentration on minimizers. So in order to look at that problem, in fact, what we look at the Euler-Lagrange equation satisfied by the minimization problem. So as I told you before, we proved that the minimizer is obtained in that class of rho, a radially decreasing function that is interval plus possibly a Dirac mass at the origin with certain mass m star. But we are minimizing, remember, in the set of probability measures. So the total, we're minimizing among functions that are of the form San L1 density plus a Dirac at 0. So the total mass is fixed, is 1. So that's why when you minimize, you have to, and you write the Lagrange conditions, you have to add some Lagrange multiplier that is associated to this mass constraint. Believe me that the Euler-Lagrange equation that you obtain for the absolutely continuous part of that measure for rho star, it looks like this. So it looks like rho star to a power m minus 1. Remember, m is less than 1, so this is negative here. Is equal to this convolution with the rho star plus the term that comes from the Dirac, which is this modulus of x to the k times the mass, minus the moment of rho star, the k moment of rho, plus the Lagrange multiplier, which is nothing else than the value of this quantity at 0. Okay? This value of this quantity at 0 is larger or equal than 0, and it can be 0 when rho star is plus infinity. Remember that we said that rho star is just a radially decreasing function that is integral. So in principle, it could come from value plus infinity at 0. There is no contradiction on that. So that is the Euler-Lagrange equation that you have. So the question that we ask ourselves is something simple than trying to find all the ranges in which you could possibly have a Dirac delta. We started, is this really possible? So we chose the easiest possible example. What is the easiest possible example? Here we have modulus of x to the k. So we can start with k, that is something that we can expand with lower polynomials. So the easiest is to start with an even integer here. So you could start with a k equals 2, but k equals 2 is trivial. You can see that it will never be in the good range that we are discussing. So the first even integer that you can look at is k equals 4. And why I'm saying that it's easier to look at even integers, because if k equals 4, this x minus y to the power 4 that I will have here, I can span it in fourth order polynomial plus the second order polynomial plus the zero order monomial, because the function rho star is radially symmetric. The odd powers will not show up, they will be 0. And in that particular case, the whole Euler-Lagrange condition that we have here that looks terrible, it simplifies a lot. It becomes of this form. The right-hand side that I had here, at every x has to be a polynomial of degree 4, but a very particular polynomial of degree 4 is modulus of x to the 4 plus a constant modulus of x squared plus L. And both L and B have to be determined by the constraints. L is determined by the mass constraint, and B is determined by this relation. B has to be related to the second order moment of the own density, rho star. So what you get is a kind of one equation that you have for rho star, in a sense, with two constraints, this one and this one. And you have two constants to determine. So if you are lucky, you may have a way of obtaining B and L in a unique way. If that's the case, then all the possible candidates to be the minimizer of your free energy function will be reduced to 1. And then you can check if that absolutely continuous part satisfies the conditions that you have or not. So that's essentially the way in which we attack the problem. We use this this constraint in order to get rid of one of the constant and write B in terms of L. And then once we have reduced it to one of the constant, we look at the other constraint, which is the mass constraint, and we see if we can have that the mass of this absolutely continuous part is less than 1, because it cannot go over 1. If it goes over 1, it's not a good candidate, because the integral rho plus m, which is a quantity between 0 and 1, has to be 1. So if this integrates to something that is between 0 and 1, I will have a unique candidate. And if it's exactly this integral is less than 1, it has to have a Dirac part, because I will be missing part of the mass to have a candidate. So that's the way in which we attack the problem. And in fact, for k equals 4, we are able to obtain this result that tells you that there is a critical value of m in which the behavior changes. The critical value of m is explicitly known in terms of the dimension. And then what you can prove is that if for k equals 4 and m between the two values in that diagram that I had before, that is d over d plus 4 and d over d plus 2, then the free energy emits a unique minimizer, which is of the form rho star plus m star Dirac at 0, with rho star a radial function. The mass on the Dirac is not present. So there is no Dirac at 0 if the dimension is less or equal than 5. But as soon as dimension is larger or equal than 6, then this number kicks in. And when you are, this number is always in between these two. And when this m is between this and that, then we have a positive mass at the origin, which is given by that expression. And when m is larger, still there is no concentration. So the answer to the question that we had before is that yes, concentration can happen. And moreover, let me, for k equals 4, we can prove it. And moreover, we can say that if there is concentration, then the density has to be the absolutely continuous part of the measure, the rho star, has to be of this form. So L has to be 0, and it has to be it has to have a singularity at the origin, although interval. It has to be of that particular form. So that's essentially what I wanted to explain to you, that we are able to prove this concentration. So let me conclude with some take-home messages. So I hope to have convinced you that aggregation-diffusion equations are a very large family of equations with different behaviors. In the case of homogeneous pressure and kernels, we can identify the regimes, and they have been identified more or less clearly, although still there are several open problems, but it's fairly understood, it's fairly well understood. Particularly in the fair competition regime for the generate diffusions, we have this dichotomy very similar to the classical Keller-Segal model, in which the L1, or it can be called L1 critical. For diffusion-dominated regimes, in the generic case, I didn't discuss that much, but you can show that the free energy has non-trivial minimizers. So that's why, in that case, there is a balance between attraction and repulsion. But the main information today is that in the fair competition regime doesn't exist for the fast diffusion case with a dichotomy. There is not this kind of criticality for that fast diffusion. You go from minus infinity for the infimum of the free energy to something that is finite through this kind of possible concentration of the mass on a Dirac at 0 with a part of the total mass of the system. And for that, the proof of these reverse HLS inequalities are crucial to characterize exactly that part of the regime. Concerning the concentration phenomena, we have proven that it happens for k equals 4. As you can see, even in my theorem before, we were very optimistic. We wrote here m as a function of k, and we say, okay, m when k is 4, we have the number. But in fact, we are not able to yet to show what is the range for any other k. We don't have a proof for any other k where is the critical value. And the difficulties, I mean, this is really an open problem. We expect to have we have done plenty of numerical simulations in which we have proven that there should be a curve, m as a function of k, that divides these two regimes. And in fact, you can prove that a curve should be there present for any dimension. Only for k equals 4, you don't have any because the curve is below when dimension is larger or equal than 5. But we check, for instance, that k equals to 10 will be enough to have already this phenomena in dimension 3. So, but we don't have a theoretical argument how to find yet this critical boundary between the two regimes. Let me just finish, conclude my talk by just, referring, making a list of the references that I have used for my talk today. Mainly, the main results I have shown you today are related to the third and the fourth reference, in which we studied together with Matías Delgadino, Jean Durbeau, Rupert Frank, and Franka Hoffman, the reverse HLS inequalities. And then we proved the concentration for k equals 4, together with Matías Delgadino, Rupert Frank, and Mathieu Levin. And with that, I thank you very much for your attention.
Thank you very much, Jose Antonio, for your nice talk. We will open the microphones for people that has questions or comments in the chat also, please. And well, you were exhaustive, so you talk about all the open problems. So all my questions were like this function of k and that.
I can, yes, I mean, related to the function of k you're interested in, I didn't explain that much, but
Okay.
I can show you, if you are interested in on that particular question. Yes, let me go to one figure here.
Yes.
Yes, so this is to check numerically what happens with this concentration for even integers. So for k equals 4 is where we prove that we have this concentration for dimension larger or equal than 6.
Yes.
Let me not enter into the explanation of this curve that much, but the only important thing here is that each of these curves represents one dimension. Okay, so this is n equals 3, dimension 3, 4, 5, 6, 7. And the important thing is the crossing with the x-axis. If the crossing happens to the right of the vertical axis, it means that there is no concentration.
Okay.
With the numerics that we are doing, if we are to the left, it means that there is concentration. Okay, so for instance, here you see the first one in which the crossing is to the left of the vertical axis is dimension 6.
Okay.
So these are numerics that compute the value of the mass of the absolutely continuous part of the candidates of the Euler-Lagrange equation. And then it tells you that when k is equal 6, you could be able to prove that there is concentration already in dimension 4, but not in dimension 3.
Okay.
By the way, in k equals 6, you can also say, okay, you can develop the 6th power into smaller powers, 6, 4, 2, and 0. You can do that, but then you have 3 constants, and still you have only 2 constraints.
Okay.
So the difficulty is that you can reduce to a 1-parameter family. So then it's much more difficult. We don't find a proof to pinpoint the right. We have a 1-parameter family of candidates, and then it's much more difficult to close our argument. We don't know how to close the argument when we have so many candidates. But numerically, it's clear that should happen. And for k equals 8, you see that the crossing looks, it's not so clear, but if you do a zoom here, the crossing is still to the right. So k equals 8 is not enough for concentration in dimension 3, and k equals 10 is already good. So that's our conjecture at the moment. And you could, of course, this is only for even integers. We did also numerics with general k. They are different from the numerics that we use for even integers because this uses that particularity that you can expand, and then it's much more accurate. But nevertheless, you can see the same behavior. So you should have a continuous curve making the difference between the two. But we don't know how to characterize the variation of.
Okay, thank you very much. So, are there any other questions or comments? No? Well, thank you, Jose Antonio. Thank you
My
again.
pleasure.
Bye.
Okay.